Okay, so now what we need to do is we need to talk about vector line integrals. So what a vector line integral is it's a line integral, but instead of just over, say for example, just the xy plane, what we have is we have a force field, or we have a vector field, and we're evaluating the value of the integral over that entire force field, or over that vector field. And so where this comes into play is doing things like work, or sometimes, in electromagnetism, or, magnetic fields, things of that nature. And it actually is a really important application of the use of line integrals and the use of multivariable calculus. So what we're going to do now is we're going to talk about the basics of vector line integrals, and then I'm going to put together another video on the applications for line integrals, because I think that's really important to look at as well. So the first thing we want to talk about is the orientation of a curve and also closed curves. Because now that we're working in vector fields or force fields, it's actually really important for us to consider the orientation of the curve or the closed curve, or a closed curve. So the first thing, we've got this closed curve, and what it means to be a closed curve, okay, and this will actually come in very important, very handy, is that we're going to move over the curve, okay? The curve is closed because essentially, if you imagine you've got your function f of x, or f of t naught, right? Our beginning time, f of t naught, is then going to end up equaling f of t n, so our ending time. And so essentially, like, we imagine we're going to have our time t, but it's going to end and start in the same location, okay? That's what makes it a closed curve. In addition to that, we're only going to be moving over the closed curve once. All right, so that's really important too, because if you move over the closed curve twice in finding your line integral, you end up with some very funky things happening, right? And you end up kind of like double counting your integral in many ways. Okay, so there's a closed curve. We want to get that idea of a closed curve, and that's what we mean. In addition to that, we should also talk about the orientation of the curve. And you've seen this before, but we can imagine that either, depending upon the parametrization, we can either, say for example, move in this direction on the curve, or we could actually move the other direction in the curve. Okay, so either we are moving forward, say for example, or actually that would be backward in the curve, or we were moving forward on the curve. All right, and that would be considered our orientation of the curve. When we're looking at vector line integrals, how the curve is oriented is going to end up becoming very important, right? So if I imagine my curve going, basically from the positive x-axis to the negative the negative x-axis to the positive part of the x-axis, then we might call that C, okay? And then if I'm moving backwards, right, I'm moving down this way, we might call that curve orientation negative C. So the curve is the same in both cases, but its orientation, the direction that you're going on when you're parametrizing it, is actually opposite. We've got C and negative C, and both of those terms are going to be really important for us as we start talking about vector line integrals. Now we want to talk about work. And the reason why we're going to talk about work is because work ends up becoming the key metaphor that we use in thinking about line integrals, right? It is kind of like this fundamental overarching idea that's going to allow us to leverage line integrals. In fact, it's kind of where the line integral came from. And so what we're going to start is with this idea of work. And so, like, we'll imagine that f of x that's a variable force, okay? And if you remember from your single variable calculus class, if we take the integral from a to b of f of x dx, okay, this is the work done on the particle moving from a to b. So we know that. So we've got that moving from a to b, right? We've got the integral a to b of f of x dx. Now, what I'm going to do now is I'm going to imagine, okay, that I've got a vector field. Okay, so like let's imagine it's a three-dimensional vector field. Okay, I got a three-dimensional vector field. I got a bunch of these vectors. They're doing whatever they're doing, right? Okay, and then I'm going to run a curve through this three-dimensional vector field. So wherever that curve goes, okay, wherever that curve goes, it's going to be intersecting something somewhere inside of that vector field. So like I've got, for example, this point right there, okay? We know the value of the vector field at that point is going to be f of x, y, z, right? Okay, so we've got that idea. Now, we're going to utilize that vector field. That vector field is going to end up being our force, right? So our force is going to be thought of as F of x, y, z, okay, at that particular point. And then what I'm going to do is I'm going to imagine, so I've got my curve, or not imagine actually, my curve is going to have a tangent vector. So that's t. This thing here is t of t. So we'll imagine we've got my force vector doing whatever it's doing, who knows, okay? And then I've got my tangent vector to the curve, okay? So we'll call this t of t, right? And this is tangent vector to the curve. And then what I'll do, so that's going to give me the direction that the particle is moving in. So let's say, for example, the particle is moving in this direction. And then I'm going to take a little cut. I'm going to take a little cut from that curve, and that's going to be delta s. Okay, that's the little cut from the curve. And so if I take t of t, if a t of t is small enough, okay, we need t of t to be small. We take t of t times delta s, okay, that's the displacement of the particle. Okay, so that's going to be the displacement of the particle. We're going to think about it that way. And then we've got this force that's being acted on it. Now remember, if you remember from like the very first chapter that we worked on, and where we were working with the kind of the vector calculus, that work, like the work vector, or excuse me, not the work vector, but work is going to equal the force, right, okay, dotted with the displacement. So the force dotted with the displacement. So we learned that before too, okay? So work is going to be force dotted with the displacement. And so we'll imagine for the work being done like over the region delta S. So we're going to move delta S, okay? So in moving delta S distance, what we're going to get, our force is going to end up being F, right? F of xyz, so the value on the force, the value of the force vector, wherever it's located, dotted with, and this will be delta s, because that's the magnitude, times t of t. Okay, and you imagine you can do that for like everywhere on this curve, right? Okay, and you'll see like if we, you know, you go read a book and they've got like, you know, they're really, really. You know, the formal, we can xi star, yi star, zi star, right? That's a particular point in delta s, okay? And then t of t, and we call this delta si, because it actually is the displacement somewhere along the line integral. Remember, it doesn't matter actually how long that piece is, okay? And what we're going to do is we're going to imagine that these are small, okay? And then, like we've been doing with every other integral, we're going to add them all up. We're going to add them all up. We're just going to accumulate all of them. Oh, I guess we should call this t of t. We're going to rewrite that as xi star, yi star, zi star. Okay? Because that's just the tangent vector there. All right? And so if we go in, we add them all together, right? We sum up the f of xi star, yi star, zi star, okay, dotted with, and I'm just going to actually pull my scalar out to the back. We're going to dot this with t of xi star, yi star, zi star, delta s, okay, and I take the limit as n goes to infinity, okay, and just for rigor's sake, I equals 1 up to infinity. For all of those, we're just taking all of them, we're adding them all together, like we've done a million times thus far. Okay, excuse me, I equals 1 up to n. Take the limit as n goes to infinity. So we're going to take really small pieces, add them all together, and then what do you get? You get an integral. This is going to end up being the integral over some curve c, and this is going to be f dot t ds, right? F dot t ds. And that is how we are going to actually calculate our work. Our work is going to be calculated as f dot t ds, all right? And we're going to use that in order to help us define the line integral. So first step, boop, there it is. Like, write it down. So now what we're going to do, we're going to take that work equation, right? Work equals the integral along the line C of f dot t ds. Okay, and what we're going to do is we're actually now going to give ourselves an alternative version that actually may be a lot easier to calculate or compute. And so we're going to suppose, okay, we're going to suppose that C is a vector equation given by R of t. Okay, so given by an R of t, and so R of t, if you remember, is going to equal, right, it's going to end up equaling, right, some x of t, y of t, z of t. All right, so that's basically, that is our curve, excuse me. And then if you remember, since our curve is R of t of t is going to end up equaling, R prime of t divided by R of t. Okay? Or divided by the, not divided by R of t, divided by the magnitude of R prime of t. So it's R prime of t divided by the magnitude of R prime of t. It's a unit vector in the direction of the tangent line. And ds, right, because ds is the derivative of the arc length, is then going to be the magnitude of R prime of t. Okay? The magnitude of R prime of t dt. Just to remember, the reason why this is the case is remember that R prime of t, okay, is going to end up equaling x prime of t, y prime of t, z prime of t. Okay? So the magnitude of R prime of t is going to end up equaling the square root of dx dt squared plus dy dt squared plus dz dt squared. And that, and then we add a dt to it, and that is ds. Okay, so that's going to end up being ds. So what that means for us is that my work is going to equal the integral along C of, and this will still be f, and it's going to then be dotted with R prime of t over the magnitude R prime of t, which is just a scalar. Okay, all of that times R prime of t dt, which the magnitude of R prime of t dt. So if we cancel out our scalars, we end up with the integral C f dot R prime of t dt. Now, just to make sure that this is formalized, remember that f is a function of basically xyz, and so we have along the integral, we got the integral along the curve C of this, actually along this curve, is going to end up being the integral from a to b of f of R of t, okay, because that's going to parameterize our curve, dotted with R prime of t dt. And that actually ends up becoming the a common way that we're going to go out and find the line integral over a vector field. So let's take a look. We want to find the work done by the force field f of xy equals x squared I minus xyj. And moving a particle along the quarter circle cosine ti plus sine tj, 0 less than or equal to t less than or equal to pi over 2. So my curve is R of t equal to cosine t plus cosine t sine t. Remember, I'm going to need R prime of t. So R prime of t is going to end up equaling negative sine t cosine t. All right. Here's my force vector. So F dotted with R. Okay. And actually, I'm going to have to evaluate F for cosine and sine. So actually, I'm going to take F of R of t is going to end up equaling x is cosine t, so it's going to end up being cosine squared t I minus cosine t sine t j, which equals essentially cosine squared t comma negative cosine t sine t. So that's going to be f of R of t. Now we'll take the dot product, f of r of t dotted with r prime of t, and that ends up equaling cosine squared t, negative cosine t, sine t, dotted with negative sine t, comma cosine t. This ends up equaling, this is going to be negative sine t cosine squared, negative sine t cosine squared t plus negative cosine squared t sine t, which equals negative 2 cosine squared t sine t. So that's f dot dr, well, pretty much f dot dr. We're going to take the integral then, and we're going to go from 0 to pi over 2. And this is going to be for 2 cosine squared t sine t dt. And just a quick u substitution, we'll let u equal cosine t du, thus is going to equal negative sine t dt. Oh, by the way, this is a negative, pardon me, negative sine t dt. So this is going to give me that negative du equals sine t dt. I'm actually going to change my bounds. So I'm going to have u of 0, which equals cosine of 0 equals 1. And u of pi over 2, which equals cosine of pi over 2, is going to equal 0. So what I'm going to get now is I'm going to get the integral, okay, from 0 to, or excuse me, not from 0, but from 1 to 0 now. And we're going to have negative and negative, so that's going to be a positive, and it's going to have the 2. And then we're going to have u squared du. This ends up giving me 2/3 u cubed evaluated from 1 to 0. So that gives me 0 minus 2/3 times 1 cubed, which equals negative 2/3. All right, I decided to do a little integration. Felt like I would have some fun. There we are. So it's negative 2/3. Notice, a couple things just to notice here. We'll do some more examples. We took first, well, what we first did was we had r of t. We took its derivative, okay, to give us r prime of t. Then we went in and we plugged in r of t into f, okay, to give us our parametrization of f in terms of t. Okay, then we dotted that value with the derivative of r, okay, and then we integrated along t, so in this case 0 to pi over 2 in that integral, and then solve the integral. And that's it. That's what you're going to do. So let's take a look at another one. All right, so let's find the value of the line integral where c is the semicircle parameterized by r of t equal to cosine t sine t, 0 less than or equal to t less than or equal to pi, so we're on the top half of the semicircle, and f equals negative y to x, okay, or negative yx. So what we need to do first, right, we've got r of t is going to equal cosine t sine t. R prime of t then is going to equal negative sine t cosine t. Okay. F of r of t is then going to equal negative sine t cosine t. Basically just plugging in r of t into f. So f dot r prime of t is then going to equal negative sine t cosine t dotted with negative sine t cosine t. And this ends up equaling sine squared t plus cosine squared t, which equals 1. So my integral, I'm now going to have my integral is going to go from 0 to pi, and it's going to be 1 dt. Integrate that. I got t going from 0 to pi, and I get pi. That one's really simple. Maybe we'll do another one that's a bit more complicated. So now let's look at this. We want to find the work done by the force field. F of xyz equals x plus y squared I plus xzj plus y plus zk along the curve r of t equals t squared I plus t cubed j minus 2tk. So we'll get that r of t, is going to equal then t squared t cubed negative 2t. R prime of t then is going to equal 2t, 3t squared, and negative 2. F of r of t is going to end up equaling, we're going to get t squared plus t cubed I plus t squared times negative 2t j plus t cubed minus 2tk. So f dot r prime of t is going to end up equaling t squared plus t cubed negative 2t cubed and t cubed minus 2t dotted with 2t, 3t squared, and negative 2. We'll go through, we'll do that. We're going to get 2t cubed plus 2t to the 4th minus 6t to the 5th minus 2t cubed plus 4t, which ends up equaling, we got 2t cubed and negative 2t cubed, they go away. I get negative 6t to the 5th plus 2t to the 4th plus 4t. So my integral, my line integral is then going to be just this, dt. So it's going to be the integral from 0 to k, excuse me, 0 to 2. 0 to 2, negative 6t to the 5th plus 2t to the 4th plus 4t dt. And then we just go, we integrate that, we evaluate. Okay? So, oftentimes the challenge of some of these things is actually to figure out what the parametrization of the curve is. If you're given the curve, then it's pretty much straightforward. It's find r prime of t, dot that with the the vector field parameterized for the curve, and then take that dot product and plug that into the integral. Okay, with your bounds being the bounds for t. Okay, so we're going to look at another formulation for the line integral, and this formulation is going to be, it's going to be related to our alternative formulation for the force field or the vector field f. So remember that we can write our f, okay, f could equal, basically we wrote it as p of xyz, q of xyz, and r of xyz, if we were looking at it in 3 dimensions. Okay, in 2 dimensions we had it actually written as f equal to, and it was just p and q. So p of xy and q of xy. Okay, and so we actually formulated it that way. Now, what we've seen before now is we have then also r prime of t dt. Okay, that's going to end up being, well, if r of t, if r of t ends up equaling x of t, y of t, z of t, then r prime of t dt is going to end up being dx dt, dy dt, dz dt, and then that's times dt. So what we get there then is we just get dx, dy, dz. Now our integral, remember, we're going to take f, dot it with r prime of t dt, okay? And so f dot r prime of t dt then is going to equal, it's going to be, we'll call this p, q, and r, dotted with dx, dx, dy, dz, and that ends up giving me pdx plus qdy plus rdz. And so my line integral now, my integral of f dot dr which is how we've been formulating this, is going to equal the integral of Pdx plus Qdy plus Rdz, all three of these over this curve C. Okay, and so this is just an alternative formulation of the line integral, a very common one that we'll see in a lot of different higher level theorems that we're going to be looking at, and also in some different applications. So let's suppose that we want to find the value of this line integral, and it's the integral along C of z dx plus x dy plus y dz. Now, what you'll see is that this is the form Pdx+Qdy+Rdz, okay? And then r of t is going to equal t squared root t, and we'll evaluate from t greater than or equal to 1 and less than or equal to 4. So this is my x, just to remind you, this is my y, and this is my z. That's my parametrization. So I just need to find dx, dy, and dz. Well, dx, we're going to take the derivative of x with respect to t. It's going to be 2t dt. dy is going to equal 1 over 2 root t dt. And dz is then just going to be 1 dt. So I'll rewrite my integral. My integral is going to go from 1 to 4. And I'm going to have it's z dt, so that's going to be t, or 2 times 2t dt. We'll write that out. Plus x is t squared, so it's going to be t squared times 1 over 2 root t dt, plus, and then y is root t, so it's going to be root t dt. Put them all together, we're going to get the integral from 1 to 4 of 2t squared plus t to the 3 halves over 2 plus t to the 1 half, all of that dt. Go in, integrate, and you got the value of your line integral, okay? So a lot of this just depends upon us recognizing that this is x, this is y, this is z, and when we talk about dx, dy, and dz, we're talking about it along the lines of like what we saw in single variable calculus, right? Take dx, you get 2t dt. Take dy, right, it's the integral of t, and then you've got the dt on it, and dz is just, in this case, 1 dt, okay? And that's evaluated in the line integral if it's in the form of Pdx, right, plus Qdy plus Rdz over our curve C. All right, so now we want to get into just some properties of vector line integrals that are going to be kind of handy for us. So we're going to let f and g be continuous vector fields. So now we've actually got two separate vector fields that we'll be evaluating vector line integrals along, with domains that include the oriented smooth curve C. Okay, and for whatever reason we could have, there could be a lot of reasons why we have two vector fields. But the first thing we want to get is that the integral over C of f plus g dot dr is going to be the integral over C of f dot dr plus the integral over C of g dot dr. So we can actually do them separately and then add, rather than adding first and then taking the and then finding the line integral. We have a scalar multiplication property, basically, that says if you multiply the vector field by a scalar, you can actually factor out that scalar and then take the line integral, right? Kind of like a property of integration we've seen before. This next one is actually very, very important. And the next two are actually really important. We have f dot dr over negative c is going to be negative along c of f dot dr. So this is the reverse orientation. So remember, negative c is the reverse orientation of c. Okay, and so that actually might come in pretty handy for us. And then we suppose that c is a piecewise smooth curve. So piecewise smooth, right, meaning that we can break it up, right? So for example, something might look like this. This is C1. We have this second piece here, we'll call that C2. This third piece we call C3. We imagine that's piecewise smooth because we have connecting points, right? Pieces connect. They're not all the same function, but we connect along the curve and adjoin the curve. It's continuous, all right? And if we do that, and we have that our curve C is just C1 plus C2 plus Cn up to Cn are smooth curves, such that endpoint of Ci is the starting point of Ci plus 1, just like I drew it right here, then what we can do is, rather than finding the line integral, okay, over the field for the entire curve, we can break it up into its component curves, and that might actually end up being a lot easier, okay? So, like, that's kind of the idea of this third one, is it allows us to kind of break up those fields. It allows us to break up the curves along the vector field and see if we could actually create something that might be easier to integrate. All right, so let's suppose that we want to find the value of an integral c of f dot tds, where c is the rectangle oriented counterclockwise in a plane with vertices 0, 0, 2, 0, 2, 1, and 0, 1, where f, our force field, is x minus 2y, y minus x. So what we're going to do here is we're going to orient counterclockwise, and so consequently that means that I'm going to travel down here. I am going to start at 0, 0, and then we are going to be moving in the direction of in a counterclockwise direction. Okay. So what I want to do first is I first want to parameterize each one of my curves. So I'm going to start out. I've got C1. And C1 is going to have, I'm going to take t greater than or equal to 0, less than or equal to 2. And basically, y is constant, so y equals 0. And we get that, then we'll let x equal t. Okay, there's its parameterization. And let's figure out what f is. So f is just going to equal t, comma, negative t. So we get t, comma, negative t. And then if I actually find I've got r prime of t, now remember r of t is just x of t, y of t. R prime of t is going to be 1, 0, right? Because it's going to be the derivative of x and the derivative of y. So there's 1, comma 0. And so what I've got now is I've just got the integral from 0 to 2 of t, comma, negative t, dotted with 1, 0, dt. Okay, and that's the integral from 0 to 2 of just t dt. So that's my first integral. That's going to be this section right here. Next up, we're going to do C2. So C2, we'll look at the parameterization here. We've got that x equals 2. That's going to be the constant value. Y is going to end up equaling t. And if we do that, then we're going to have t is going to go from 0, t is greater than or equal to 0, and less than or equal to 1. So f then is going to equal 2 minus 2t, and then we'll get t minus 2. And r prime of t is then going to equal 0, comma 1. So our integral then is going to be the integral from 0 to 1 of 2 minus 2t, comma t minus 2, dotted with 0, 1, dt. And that is then just going to be the integral from 0 to 1 of t minus 2 dt. So now I've got C3. So C3, what we want to do here, notice that C3, okay, is, if we were to actually go in this direction, if we were to orient it in the direction that it's oriented in, okay, then what we would get is we'd have kind of like a slightly more complicated parameterization, all right? The simple parameterization is actually going here in the clockwise direction. The simple parameterization there is just simply that y, we have y equals 1, and we have that x equals t. Okay, so if we take y equals 1, x equals t, that's great. And then we go from 0 to 2. So t less than or equal to 0, less than or equal to 2. Okay? But it's in the wrong direction. Okay? It's not in the right direction. So what do we need to do? We're going to use that property that actually tells me that the integral that I'm looking for, okay, if I take its opposite orientation, I just have to make it negative. And then I get the actual orientation that I want. So what we're going to do here is we'll find f. F is going to then equal, right, t minus 2, comma, and then 2 minus t. R of t is going to then equal or r prime of t is then going to equal 1 comma 0. Okay. And just remember, right, because we want to figure out C3, but we're actually doing the negative, so this is now the negative of the integral from 0 to 2 of t minus 2 comma 2 minus t dotted with 1, 0 dt. And so this is then negative integral from 0 to 2 of t minus 2 dt. Okay? Because we're actually, this is the opposite orientation, so we have to make it negative, right? Use that property to make it negative. And then I'm going to do the same thing here with C4, because C4's easy parametrization is just to, let x equal t and let y equal 0, or excuse me, let x equal 0 and let y equal t. So for C4, we're going to let x equal 0 and then y equals t, and we're going to go from 0 less than or equal to, t less than or equal to 0, less than or equal to 1, okay? And so then our force field is going to be F is going to equal negative 2t, comma, and then t minus 0 or just t. T, okay? And then r prime of t is just going to equal 0, 1. So we're going to take the negative integral from 0 to 1 of negative 2t t dot 0, 1 dt, which equals the negative of the integral from 0 to 1 of t dt. So those are the 4 line integrals along those lines in this force field. And now all I need to do is just add all of them up. So the integral along C of f dot dr is going to equal the integral. First one is going to be 0 to 2 t dt, 2 t dt, plus the integral from 0 to 1 t minus 2 dt, plus negative integral 0 to 2 t minus 2 dt. Okay, and then, or we could just make that a minus. We'll just make that a minus, and then minus again the integral from 0 to 1 of t dt. Okay, which, by the way, I mean, like if you kind of look at this, right, what can we do? We could actually say, oh, look, that's 0 to 2, 0 to 1. I subtracted that out. I mean, basically, it's going to be the integral from 1 to 2 of t dt plus the integral from 1 to 2 of t minus 2 dt, and that'll be your answer. So it actually simplifies out quite a lot. Okay? So in this particular example, 1, we broke up our integral into 4 separate line integrals, and 2, we simplified our parametrization by using that idea that we could reverse the orientation and make our line integral negative. So this completes our fundamental exploration of line integrals. What we talked about here today is we talked about this basic relationship between work and how we get the line integral over a vector field. When we talk about the line integral over a vector field, probably the easiest way to calculate that is to find the force vector along a vector path r of t, so f of r of t, and then dot that with the derivative of r of t, and then take the integral of that, all of that along some value t. And that's basically all we really did. We didn't utilize really f.tds because that actually can be kind of difficult to work with. Although theoretically it's actually very important, it's very, very powerful. It's not really practical from a calculation standpoint. It can get a little unwieldy. So what we've done here is we've actually talked quite a bit about lots of different ways that we could think about our line integrals. How do we calculate line integrals? Previously we've talked about how do we do scalar line integrals. Now we've got vector line integrals from a lot of different perspectives, right? So go in, practice so that so that we can work with these in other circumstances.